Hello student, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to be taking the class of topic on embedded system, and in the previous lecture I have been describing the finite state machines and how it works, what is the significance of finite state machines on embedded system. We are going to discuss and we are going to continue this lecture and discuss the same thing that we were discussing earlier in the lecture. So let's start with the lecture. So as we are discussing in the earlier section, that we have described how the finite state machine works, how the software, the coding is working to understand the significance and how it works. But we have a clear cut knowledge how the programs works and what the finite state machines diagram has shown us, and we have also described it with coding technology. So let's go to the next slide, and here we have here is that HCFSM and the state chart language and hierarchy. And the HCFSM, the full form of HCFSM is the hierarchy extension in finite state machine, which allows to decompose the state machine into another state machine or a group of states into a new hierarchical states. Now, without the hierarchy, we have this, that this is the idle state. Now, this is how it works. This is the going up state and this is the going down state. And as the door open, then the fire going down and the fire door open. So this is clearly a haphazard pictorial depiction where we don't have any hierarchy. Now, if we use the hierarchy extension FSM, it will provide us the state chart language, and it will help us to organize the whole state machine data flow. Let's go to the next slide. Now, if we have a hierarchy contestant here, that the same state machine that we have described in the earlier or the previous lecture, where we have how the state machine works and the programming condition that has been met there. And now if we just go back to the slide here, we have this specific finite state machine here. We have a condition. According to the condition, the data state will go from the idle state to the going up state, or the idle state to the going down state, or it will jump from the going up state to the door open state, and vice versa. So we have already discussed how the state machine works. So if we just go back to here, and if we just go back to here, that where we have introduced the hierarchy contention, hierarchical states, hierarchical extension in HCFSM, which is also known as this H for the hierarchy here. So this is the picture which depicted the non-hierarchical state machine. Now, if you just go back to this is the hierarchical state machine, where the going up, the idle state, and the transfer from the data from the one state to another state. This is the condition. This is the block. Now, this going down block has been connected to the fire mode, where the fire going on state and the fire door open state are also recursive and non-recursive state, and are both have different purpose, but both are also connected to each other. So that's why the hierarchical strategy has been applied here, and here you can see that whole structure looks much more organized. So let's go to the next slide. Now, this is the using concurrency in hierarchy convention extension FSM, where this is the normal mode, this is the unit control, this is the normal mode, and this is the fire mode. Okay, request resolver. So let's go to the next slide. Now, this program state machine model has been described here, is that it allows the programmer to use sequential code to define state actions. including extension for the complex data types and variables. It includes hierarchy and concurrency. A SPM having only one state is called the program state terminology. A PCM having many states whose actions are just assignment statements is equivalent to HCFS. Now, elevator control. Now, if you have elevator control, in case of unit control, we have normal mode, up and down is equal to 0, open is equal to 1. While one condition met, the while require is equal to floor, then the open 0 format is open. And if require greater than floor met, the up is equal to 1 will go on, and else down 1 will go on. So basically, we have the state machine model or the data flow graph. You can say it, you can take any names. Now, in the previous lecture, we have described model where we have used the coding technique to describe the specific functionalities of the specific state machine model. Now, just to revise the state machine model, we have used a different program state machine model. That we have already got the description of the detailed description of different kind of models. The first model was the sequential model. Now, this model was the program state machine model. It will be also in work where it will be also providing us the same logical expression but using lesser amount of data or the lesser amount of mathematical complexities or hardware complexities. So using this technique, we can easily obtain the same specific data flow model that we are required to build. So this is the lecture, and we also knows that this is the fire model. This has been here. All the state is related to each other. Let's go to the next slide. Now, PSM includes two types of transition. One transition is the transition immediately. Transition takes immediately if the condition is true. And the transition on completion, transition takes once the requested task is completed. Now, as you can see here, the transition immediately, it means the transition takes immediately if the condition is true. This is the one point that we are making here. Okay. The another is that we have transition in completion, where the transition takes once the requested task is completed. The role of appropriate model and language. The model represents the system while the language captures the model, and language have the constructs which captures the model. So role of appropriate model and language. Model represents the system while the language captures the model, and the language have constructs which captures the model. The language has captures which capture the model. Okay, and vice versa. So as we have described here. So let's go to the next slide. The concurrent process model. The concurrent process model that has been said here is a system functionality is described using multiple computation models. The first, it allows to describe the functionality of a system in terms of two or more concurrently executing subtasks. It uses the multitasking schemes. Now, we are going to describe how the multitasking schemes are occurred. Okay, first one is that it uses the multitasking scheme. It means the state machine, the sequential program, the data flow, the concurrent process. The first one, the sequential program, which uses the Pascal, C++, Java, and the VHDL. And the same thing will also be true for concurrent process. So the concurrent process uses the Pascal, C++, Java, and VHDL, and it's also be true for data flow. But yes, and also it's true for state machine. Now, the C++ is the implementation of A, implementation of B, implementation of C, and same can be said about the other three languages also. So in case of concurrent process models, a system functionality is described using multiple computation models. It allows to describe the functionality of a system in terms of two or more concurrently executing subtasks. And suppose now this line what we have described here, that it means it allows to describe the functionality of a system in terms of two or more concurrently executing subtasks. Now two or more concurrently executing in terms of two or more concurrently executing subtasks, the whole functionality of the system need to be described in terms of two or more concurrently executing subtasks. Okay, so let's go to the next slide. The choice of computation model is based on the designer to describe the system. The choice of computation model is based on the designer to describe the system. Okay. First of all, yes, we have covered this. The choice of the computation model is based on the designer to describe the system. The choice of the language is to capture the computation model used by the designer. The choice of implementation is based on whether it meets power and size and cost requirements. Now, if you have described this all three sentences, the first one is the choice of the computation model is based on the designer to describe the system. So the computation model is always going to be based on the designer of the described system. According to the system, according to the design, the computation model will be chosen. There can be different kind of computation model that we can work on, but to select which computation model will be working on the system, it will solely depends upon the designer. According to the designer, there are different kind of design, and according to that, different kind of computational model, or as per you can say, the different kind of mathematical model has been used. So these are the two complementary things. Means a computation model that is much more easier to understand. It is much more less complex, practically less complex. Maybe computation model. If we have a less complex computation model, what we will do? We will design according to that, or we can compute along with the designer. So both are basically complementary to both of them. If we can have a computation model which can be realized using a specific design and which can be very much useful, so that system will describe through the designer or through the design and through the computation model. And the second one is saying that the choice of the language is to capture the computation model used by the designer. Now, a designer, suppose design a hardware, so any kind of computation model will be used here, or probably used. So the choice of the language is to capture the choice of the language is to capture the computation model used by the designer. So which computation model has been used by the designer is the most important thing we need to understand. So now the next one is the choice of implementation is based on whether it meets power, size and cost requirement. Now the choice of implementation is based always on the power, size and cost requirement, because as we know that from the beginning of the scaling or the integration part where we have come up with in 1947 transistor, from then on, from that time, it has been a great responsibility of the designers, or basically I would say the basic challenge of a designer is to create or design some hardware complex or complex hardware designing or a simpler design depending upon the power, size and the cost. So in case of embedded system, the power requirement should reduce, the size of the system should reduce also, and the cost is also should reduce. So, but the basic problem here when we ask to reduce power, size and cost, and it sounds very easy, and people have done that. People have reduced the cost, people have reduced the power, people have reduced the size. So, but these three are very much interrelated. Now, suppose we try to uh, design a system where we suppose make the power distribution at the lowest possible level. Now, the power, okay. Now, if we have to reduce the power to zero, what we have to do? We have to reduce the power dissipation of the computational design. Now, the computational design may consist of different sizes of transistors and MOSFETs, like you can see. Now, if to reduce the power, we have created a machine, a complex machine, to reduce the use of power. To reduce the use of power and to reduce the size, both the things can't occur simultaneously. It is a tough call that we have to reduce the cost, we have to reduce the power, and we have to reduce the size. All these are simultaneously a bit tough task to ask, because if, as you are saying, that if we reduce the power, suppose if we have reduced the power, and if we have also reduced the size. Now, if we reduce the size, the hardware complexity will go on, and the power distribution practically, as we know, the space of that computational model is reduced. So, what will happen? The power distribution will increase. Now, suddenly we just decrease all the components of our embedded system, and we think the problem has solved or resolved. That is not the case. Now, suppose we have reduced all the sizes, what will happen? The power dissipation will shoot up. Now, if we have to reduce the power, now suppose we have to reduce the power, what we have to do? We have to create an environment, or we have to create a complex architecture design where the different kind of losses, the current flow loss or the other devices losses should need to reduce. But it can't be happen. So if we have to reduce the power, the size of the thing will go high, and if the thing occur, vice versa. Okay. Let's go to the next slide. The heartbeat monitoring system. Now we will take the example of a heartbeat monitoring system. The first task was to read pulse. The task 2, if V1 is between, we'll go to the task 2 later. Now first we describe the task 1. First one, the read pulse. And if pulse is L0, then activate siren. If pulse is greater than high, then activate siren. Sleep 1 second and repeat. Task 2, if V1 and by V2 processed, then L0 is equal to L0 plus minus 1. And if B3 by V4 pressed, then high is equal to high plus minus 1. And sleep 500 milliseconds repeat. So this is the heartbeat monitoring system. Same thing can be used for set-top box system. Task 1, read the signal. Separate audio and video. Send audio to task 2 and then send video to task 3 and repeat. And task 2, wait on task 1, decode output audio, repeat. And task 3 is the wait on task 2, decode output and video, decode output video and repeat. So what all this coding functionality, all the system is describing here. As about task 1, we first read the pulse. If pulse is L0, then activate siren. It means at the lower end we will activate the siren, and if pulse is high, we activate the siren. Sleep 1 second, repeat. It means first we read the pulse. If the pulse provides us with a value that which is L0, means at the lower side, we will activate the siren, and the sirens will say that if pulse is greater than high, we will activate the siren. Now if pulse is greater than high, it will also activate the siren, and sleep is 1 second, repeat. It means now both the cases, the pulse is greater than L0 and pulse is greater than high. So in both the cases, we have to sleep for once the siren will be activated, and for using the siren, it will indicate us to go to the sleep. So this is the heartbeat monitoring system. The task 2 is if B1 and B2 processed, then L0 is equal to L0 plus minus 1. and if B3 by B4 pressed, then high is equal to high plus minus 1 and is sleep 500 millisecond and repeat. And set-top box system, same thing. First we read the signal. Second, what will happen? First thing we read the signal, and second we separate the audio and video signal. Then we send the audio signal, that is the task 2. Basically we send the audio signal to the task, and after that we send the video signal to the task, and we repeat the same process. And the task 2 is wait on task 1, decode and output audio and repeat. And task 3 will do the same thing. So this is the structure of a set-top box system. This one is the first one is the heartbeat monitoring system, and the second one is set-top box system. So now we go to the next point here, where we will understand the basic operations defined by the concurrent process model. The basic operation that we will describe by the concurrent process model is process create and terminate, process suspend and resume, and process join. And the communication among processes are shared memory and message passing. And we have already described what the shared memory and message passing is. In case of shared memory, and what complexities will occur, or the deadlock, and all these things we have already described. So the communication among processes are shared memory and message passing, that we have already covered. Okay, so let's go to the next slide. And this one is the synchronization among processes. And that's also important part, is that one process must wait for another process to compute a value, reach a point in execution, or signal some condition before it proceeds. Synchronization among concurrently executing process is to use a construct, condition variables such as signal and wait. One method to achieve synchronization is to monitor. It is nothing but collection of data and methods that operates on this data, similar to an object on object-oriented programming, or OOPS. So these are the processes I am going to describe here. Okay, so let's start with that X is allowed, Y waits. So monitor data code, process X and process Y. X allowed, Y to waits. X allowed and Y waits. Okay, first one. Next, X waits and Y is allowed. So first one, the process X has entered into the monitor the data code to work on the data process everything. Process Y has wait at that point. Now next, the process X, it will wait, and the process Y enter into the monitor and the data processing happen. Third one is the process Y again in the waiting state, the process X again into the data processing space. This is now X terminated and Y is allowed. Okay, so two things which will happen. First, any one of the process will be allowed. Now after completion of this process, we can enter into the another process can enter into the system. Now also the same thing, that someone is waiting and another one is working it out. So both the condition can be met. Okay, so these are the process we are discussing here. Let's go to the next slide. And now the implementation of one is the communication bus, where the process 1 is directly to the process A, and the same thing will happen to the other. In case of general purpose, all the process will go into the general purpose. Okay, in case of, so basically what will happen, that suppose we have a application specific information process, where the processor A, processor B, processor C, processor C all do the process 1, 2, 3, 4 simultaneously. But in case of general purpose process, there are n numbers of processes. So all the processes are get into the general purpose processor. In case of application specific information processor, each processor has a different process to conduct and to complete. So all this process will get along with. And in case of application specific IC, so this is the application specific IC. In case of application specific information IP, information process, is that process 1 go to the processor 1 and all the other processes will go to the general purpose processor. Okay, so these are the different kind of implementation. And one way to implement multiple processor is to implement multitasking. Often we can encounter with multiple process to be implemented with a single processor. To achieve the above is to share the processes to many processes. During the process of sharing, the processor leads the concept of suspending and resuming the process. In order to implement the above, we need to operating system. The task of the OS is creating and terminating process, and suspending and resuming the process, joining process and scheduling the process. Okay, so we will conclude our lecture here. Thank you.